Out there, scattered across the galaxy, are objects so extreme they barely seem real. They're not planets, not quite stars, and not black holes. They are neutron stars. At first glance, they seem small, almost insignificant, barely 20 kilometers across, small enough to fit inside a city. But don't be fooled. Inside that tiny sphere is more mass than our sun. Crushed, compressed, forced into a state of matter that should not exist. This story begins with a giant, a star many times more massive than the sun burns through its fuel. For millions of years, nuclear fire pushes outward, holding gravity at bay. But fuel runs out, and when it does, gravity wins. The core collapses in less than a second. Atoms are torn apart. Electrons are forced into protons. Matter loses its identity. What remains is something new. Neutrons, packed so tightly that space itself seems to disappear. The outer layers explode outward in a supernova, one of the most violent events in the universe. But at the center, the core survives. Barely. What's left behind is a neutron star, a cosmic relic of destruction. Imagine compressing Mount Everest into a grain of sand. Imagine a teaspoon weighing 1 billion tons. This is no metaphor. This is physics. Gravity on the surface is hundreds of billions of times stronger than Earth's. Step too close, and your body would be stretched, flattened, and pulled apart, atom by atom. Yet the neutron star does not collapse further. Something stops it. Not heat, not pressure in the way we understand it, but a strange quantum resistance, the refusal of neutrons to occupy the same space. This is matter at its absolute limit, and still the star spins. When it forms, it inherits the rotation of the original star. As it shrinks, it spins faster, much faster, hundreds of times per second, a city-sized object rotating faster than a kitchen blender. From this moment on, nothing about this object behaves normally. Light bends, time distorts, magnetic fields twist space itself. Neutron stars are not just dead stars. They are laboratories of the universe's most extreme laws. And we are only beginning to understand what they are capable of, because density is only the beginning. In the next part, we descend deeper into gravity, magnetism, and forces so powerful they rewrite the rules of reality itself. Stand on a neutron star, if that were possible, and the universe would change instantly. Gravity here is not a pull. It is a command. Your body would be flattened to the thickness of a molecule, not torn apart over time. Instantly, light itself struggles to escape. Photons climbing away lose energy, stretched redder and redder by gravity's grip. Time slows. A clock on the surface ticks more slowly than one far away. This is gravity approaching its breaking point. Yet neutron stars are not black holes. They stop just short. What holds them back is a delicate balance between gravity and the quantum pressure of neutrons. But gravity is only half the story. Neutron stars possess magnetic fields unlike anything else in the cosmos, trillions of times stronger than Earth's. Strong enough to strip atoms apart at a distance. Strong enough to twist empty space into rigid shapes. If a neutron star drifted halfway to the moon, it would wipe every credit card on Earth. If you stood nearby, your atoms would stretch into long filaments, aligned with invisible magnetic lines. Some neutron stars take this even further. They're called magnetars. Their magnetic fields are so intense, they crack the star's crust. Solid nuclear matter, like an eggshell. These fractures unleash titanic bursts of energy, gamma rays that can affect Earth from across the galaxy. In 2004, one such blast briefly altered Earth's atmosphere. From 50,000 light-years away, for a fraction of a second, it outshone everything else in the Milky Way. This is power without fire, without fusion, pure magnetic violence. And still, the star holds together. The surface of a neutron star is not rock, not metal. It is a lattice of atomic nuclei locked in place by gravity so strong that matter becomes solid in ways we cannot recreate. Above it, a thin atmosphere only a few centimeters thick. Below it, layers we barely understand. Superfluid neutrons, exotic particles, perhaps something even stranger. Physicists debate what lies at the core. Quark matter, hyperons, states of matter that exist nowhere else. Each neutron star may hold a different answer, each one a unique experiment. But these stars do not remain silent. They announce themselves. They pulse. They flicker. They speak across space with clockwork precision. And when we listen, we realize something unsettling. Neutron stars are not stable. They are strained, stressed, and sometimes they break. Some neutron stars act like lighthouses. They spin. They beam radiation from their magnetic poles. And as those beams sweep past Earth, we see pulses. Perfect. Predictable. These are pulsars. They tick with astonishing regularity, more precise than atomic clocks. For decades, astronomers trusted them as cosmic timekeepers, until something strange happened. Some pulsars suddenly sped up, just a little, then slowed again. These events are called glitches. They're starquakes. The crust of a neutron star fractures as the superfluid interior shifts beneath it. A planet-sized object cracking like ice on a frozen lake. Even stranger, some pulsars slow down, then abruptly reset. No warning, no explanation. Inside, superfluid neutrons flow without friction. They form vortices, quantized whirlpools of motion. When those vortices suddenly rearrange, the star's rotation jumps. This is quantum physics playing out on a stellar scale. But the most dramatic moments come when neutron stars meet. Binary systems, two dead stars locked in a fatal dance. They spiral closer over millions of years, emitting gravitational waves, ripples in space-time itself. Finally, they collide. The impact releases more energy in seconds than the sun will emit in its entire lifetime. Heavy elements, gold, platinum, are forged in the chaos. The atoms in your body may have come from such a collision. In 2017, humanity detected both the gravitational waves and the light from one such merger. For the first time, we heard and saw the same cosmic event. But the aftermath remains uncertain. Sometimes the merger forms a black hole. Sometimes something else. A hypermassive neutron star spinning, trembling on the edge of collapse. We do not know how long it survives. Milliseconds? Seconds? Or longer? Each event challenges our models. Each observation raises new questions. Neutron stars are not just remnants of the past. They are active agents in the universe's evolution. Factories of elements. Engines of radiation. Sources of mystery. And still, beneath all this activity, their cores remain hidden. Untested. Unseen. In the final part, we confront what neutron stars may ultimately reveal, not just about the universe, but about the limits of reality itself. Neutron stars exist at a boundary, not just between life and death of stars, but between known physics and the unknown. Their cores reach densities higher than atomic nuclei, temperatures colder than space, hotter than stars, pressures beyond comprehension. We cannot reproduce these conditions. We can only observe, infer, guess. Every neutron star we find adds a piece to a puzzle we don't yet understand. Some may contain exotic matter, particles that vanish instantly on Earth. Others may hide transitions to quark matter, where neutrons dissolve into their components. Or something entirely unexpected. There may be a maximum mass, a point where neutron stars cannot exist. Beyond it, collapse is inevitable. But where that line lies remains uncertain. Each new measurement refines the boundary. Each discovery pushes it back. Neutron stars also challenge our understanding of space and time. They bend light. They slow clocks. They distort space-time just shy of tearing it open. They test Einstein's theories in ways no experiment on Earth can. And so far, the universe agrees with him. But for how long? What happens inside a neutron star may hold clues to unifying gravity with quantum mechanics, the greatest unsolved problem in physics. In a sense, neutron stars are messages. From regions we can never visit. From conditions we can never create. They speak in pulses, glitches, and waves in space-time. And we're just learning how to listen. Somewhere out there, a neutron star spins in silence. Another cracks under magnetic strain. Another prepares to collide. Each one rewriting what matter can be, what gravity allows, what the universe tolerates. And perhaps the most unsettling thought of all, neutron stars may not be the end. They may simply be the last stable step before something even more extreme. Something we have not yet imagined. The universe has not finished surprising us. And neutron stars are proof.